NENOMATICA, where mathematics meets YouTube excellence. Welcome to this mathematics video. Today we're going to solve a problem that asks us to compare two values to determine which one is larger. Let's look at our example. We need to determine which of the following two values is larger. Let's start by simplifying expression A. We have A equals the tangent of 226 divided by 17 pi. First, we'll use the periodicity of the tangent function to simplify the argument. We can write 226 as 13 times 17 plus 5. This gives us tangent of 5 over 17 pi plus 13 pi. Now we can use the property that tangent has a period of pi, meaning tangent of x plus n times pi equals tangent of x for any integer n. Therefore, A equals tangent of 5 pi over 17. Now, let's simplify expression B. We have B equals 1/2 times the logarithm base 1/7 of 2,400 and 1 divided by 36 plus 2. First, let's use the logarithm property that log base A of B equals negative log base at inverse of B inverse. We can rewrite this as 1/2 times the logarithm base 7 inverse of 36 over 2,401 plus 2. Let's continue simplifying B. We need to simplify 36 over 2,401. Note that 36 equals 6 squared and 2,401 equals 49 squared, which is 7 to the 4th power. Using the power property of fractions, we can rewrite this as 1/2 times the logarithm base 7 of 6 squared over 49 squared, plus 2. Continuing with our simplification, we can rewrite this as 1/2 times the logarithm base 7 of 6 over 49 squared, plus 2. Now we can use the property that log base A of B to the power of n equals n times log base O of B. This gives us 1/2 times 2 times the logarithm base 7 of 6 over 49 plus 2. Let's simplify the coefficient. 1/2 times 2 equals 1, so we have the logarithm base 7 of 6 over 49 plus 2. Let's continue simplifying B. We can use the logarithm property that log base A of B over C equals log base I of B minus log base I of C. So B equals logarithm base 7 of 6 minus logarithm base 7 of 49 plus 2. Since 49 equals 7 squared, we can use the property that log base of A to the power of n equals n. Therefore, B equals logarithm base 7 of 6 minus logarithm base 7 of 7 squared plus 2. This gives us logarithm base 7 of 6 minus 2 times logarithm base 7 of 7 plus 2. Let's complete our simplification of B. We know that logarithm base A of it equals 1. So logarithm base 7 of 7 equals 1, and B equals logarithm base 7 of 6 minus 2 plus 2. The minus 2 plus 2 cancels out. So B equals logarithm base 7 of 6. Now we've simplified both values. We have A equals tangent of 5 pi over 17, and B equals logarithm base 7 of 6. To compare these values, we need to find a common representation. Let's note that logarithm base 7 of 6 is less than logarithm base 7 of 7, which equals 1. Also, we know that tangent of pi over 4 equals 1. Let's convert B to a tangent value. We can state that logarithm base 7 of 6 equals tangent of pi over 4. Actually, we can be more precise. Logarithm base 7 of 6 equals tangent of 5 pi over 20. Since tangent is an increasing function in the interval from 0 to pi over 2, and 5 pi over 20 is less than 5 pi over 17, we can conclude that tangent of 5 pi over 20 is less than tangent of 5 pi over 17. Therefore, B is less than A. Welcome to our math lesson today. We'll be solving a problem that compares fractions and determines which one is closer to 1. Let's start with our example. If m is less than n, then which of the numbers m over n or n over m is closer to 1? Let's solve this step by step. To determine which fraction is closer to 1, we need to find the difference between each fraction and 1, then compare these differences. First, let's calculate how far m over n is from 1. Next, let's calculate how far n over m is from 1. Now, since we're comparing distances, we need to take the absolute value of these differences. But since m is less than n, both n minus m and m minus n are positive, so we can directly compare these fractions. Since m is less than n, the denominator m is smaller than the denominator n. With the same numerator n minus m, the fraction with the smaller denominator will be larger. Therefore, n minus m over m is greater than n minus m over n. Let's interpret this result. The difference between n over m and 1 is n minus m over m. The difference between 1 and m over n is n minus m over n. Since n minus m over m is greater than n minus m over n, the distance from n over m to 1 is greater than the distance from m over n to 1. Therefore, m over n is closer to 1 than n over m. Welcome to this mathematics video. Today, we'll be proving an inequality using algebraic manipulation. Let's start with our problem. We have the following conditions. We need to prove that a squared plus b squared is less than or equal to 2. Let's start our proof by defining a variable s subscript n as a to the power n plus b to the power n. Our first step is to compute the expression a squared plus b squared minus 2 times s subscript n minus 1. This equals a squared plus b squared minus 2 times a to the power n minus 1 plus b to the power n minus 1. Now, let's expand this expression. We get a to the power n plus 1 plus a squared b to the power n minus 1 plus b squared a to the power n minus 1 plus b to the power n plus 1 minus 2 times a to the power n minus 1 minus 2 times b to the power n minus 1. We can rearrange these terms to group them more effectively. We get a to the power n plus 1 plus b to the power n plus 1 plus a squared b to the power n minus 1 plus b squared a to the power n minus 1 minus 2 times a to the power n minus 1 plus b to the power n minus 1. Now, using our given condition that a to the power n plus 1 plus b to the power n plus 1 equals a to the power n minus 1 plus b to the power n minus 1, we can substitute this into our expression. This gives us a to the power n minus 1 plus b to the power n minus 1 plus a squared b to the power n minus 1 plus b squared a to the power n minus 1 minus 2 times a to the power n minus 1 plus b to the power n minus 1. Let's simplify this expression further. We get a squared b to the power n minus 1 plus b squared a to the power n minus 1 minus a to the power n minus 1 minus b to the power n minus 1. Let's factor this expression by grouping similar terms. First, we can rewrite it as b squared a to the power n minus 1 minus a to the power n plus 1 plus a squared b to the power n minus 1 minus b to the power n plus 1. Then we can factor out a to the power n minus 1 to get b squared minus a squared, and b to the power n minus 1 to get a squared minus b squared. We can further simplify this to a to the power n minus 1 times b squared minus a squared, plus b to the power n minus 1 times a squared minus b squared. Factoring out a squared minus b squared, we get a squared minus b squared times b to the power n minus 1 minus a to the power n minus 1. We can rewrite this expression by factoring out a negative sign. This gives us negative a to the power n minus 1 minus b to the power n minus 1 times a squared minus b squared. Now, we need to analyze the product of these two factors. Note that since a and b are both positive, and if a is greater than b, then a to any power is greater than b to the same power. This means a to the power n minus 1 is greater than b to the power n minus 1, and a squared is greater than b squared. Therefore, both factors a to the power n minus 1 minus b to the power n minus 1 and a squared minus b squared have the same sign, making their product positive. But since we have a negative sign in front of this product, the overall expression is negative or 0. Let's put this back into our original expression. We had a squared plus b squared minus 2 times s subscript n minus 1 equals negative a to the power n minus 1 minus b to the power n minus 1 times a squared minus b squared, which is less than or equal to 0. Rearranging, we get a squared plus b squared minus 2 times s subscript n minus 1 is less than or equal to 0. Since s subscript n minus 1 is a sum of positive terms, it's always positive. Therefore, a squared plus b squared minus 2 is less than or equal to 0, which gives us a squared plus b squared is less than or equal to 2. Welcome to this mathematical proof video. Today, we'll be proving an important inequality that relates to the sides of a triangle. This proof uses algebraic manipulation and factoring techniques to arrive at a remarkable result. Let's start with our example. We want to prove that for positive values a, b, and c, the following inequality holds. A to the fourth plus b to the fourth plus c to the fourth is less than 2 times a squared b squared plus a squared c squared plus b squared c squared. Now, let's solve this step by step. First, we need to move all terms to the left side of the inequality. We're rearranging the expression to isolate everything on one side. Now, let's expand the expression on the left side. We'll expand the second term and distribute the -2 factor. In the next step, we'll add and subtract the same term, 2 a squared b squared. This doesn't change the value of the expression, but it allows us to factorize more easily. Now we'll rearrange the terms to prepare for factorization. This grouping will help us identify a pattern that can be factored. Let's continue by factoring the expression. We can recognize a perfect square pattern here. Now we can perform the final factorization of the expression. We recognize another pattern that can be written as a product of 2 factors. Let's factor this expression one more time. We can use the difference of squares formula again on each of these terms. Now, let's analyze the factors in this expression. Since a, b, and c are all positive, we need to determine which factors are positive and which are negative. For the product of these factors to be negative, an odd number of factors must be negative. Let's examine when this happens. The conditions we derived are exactly the triangle inequality. For 3 values to form the sides of a triangle, the sum of any 2 sides must be greater than the third side, and the difference of any 2 sides must be less than the third side. Therefore, we've proven that 2 sides must be less than the third side. Therefore, we've proven that when a, b, and c are positive and can form the sides of a triangle, the original inequality holds. A to the fourth plus b to the fourth plus c to the fourth is less than 2 times a squared b squared plus a squared c squared plus b squared c squared. Welcome to our math video where we'll solve an interesting inequality problem. Today we'll prove that a specific fraction lies between the minimum and maximum values of a set of fractions. Let's look at our example. We assume we have n fractions in the following form: a 1 over b1, a 2 over b2, and so on until a n over bn, where all bi are positive and I ranges from 1 to n. We need to prove that the following fraction lies between the minimum and maximum values of the given fractions, the sum of all ai divided by the sum of all bi. Now, let's solve this step by step. First, we'll define m as the minimum value and m as the maximum value among the given fractions. This means that for any I from 1 to n, m is less than or equal to ai over bi, which is less than or equal to m. By multiplying all sides by bi, which is positive, we get m times bi is less than or equal to ai, which is less than or equal to m times bi. Now, let's sum these inequalities for all values of I from 1 to n. By adding all these inequalities, we get m times the sum of all b I is less than or equal to the sum of all ai, which is less than or equal to m times the sum of all bi. Finally, since the sum of all bi is positive because each bi is positive, we can divide all parts of the inequality by this sum. This gives us m is less than or equal to the fraction we need to prove about, which is the sum of all ai divided by the sum of all bi, which is less than or equal to m. And this is exactly what we wanted to prove. We've shown that the combined fraction lies between the minimum and maximum values of the individual fractions. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.